Today we are focusing on calculating equilibrium concentrations using ICE table. By the end of this video or lesson, you should be able to set up, solve and decide when to use assumptions confidently. Now in the last video we somehow did some calculations also, but also today we are going to do some calculations, and today we are going to be focusing more on calculating the equilibrium concentrations. In chemical equilibrium calculation, students usually fail not because of chemistry, but because of poor setup. So today, we master the 3 core steps and apply them to real exam style problems. So, there are three steps to solving equilibrium concentration problems. So the first one is write the balanced equilibrium equation. So for example, they might give you in a statement, maybe this and this react to form what and what. So write the balanced equilibrium equation. Sometimes they usually give it. The second one is write the Kc expression. In the previous video, we talked more on writing the Kc expression. So for example, the Kc, we said it's always products over the what? Over the reactants. So this is the Kc we are talking about. Now the last step is write an ICE table to calculate equilibrium concentrations. So for us to understand this well, we are going to be using examples. So the first example we are going to do is that one. So given a reaction, we have that should be carbon monoxide and hydrogen are acting to produce methane and water. So we have been given the data, which is the concentrations. We have been given the concentrations at equilibrium of carbon monoxide, hydrogen and water. But we have not been given for what? For methane. And our job is to what? Our job is to find the concentration at equilibrium of what? Of methane. And just as I emphasized in the previous video, that equal sign there, should be like this. Yes. So so how do we find now? How do we find the what? The concentration of methane. So as we said earlier, the first step is writing the equilibrium expression, which is already given in the question. The next step we write the what? The expression. So what is the Kc expression there? The Kc expression is Kc is equal to what? The product is CH4 power what? It has a coefficient of 1, so it's just CH4. We have H2O over what? What are the reactants? We have carbon monoxide power what? Power 1, because it has no coefficient. It has the coefficient of 1. Then we have H2 power 3, because the coefficient of H2 is 3. So that is our Kc expression. Now, just from this Kc expression, you can see that the answer we can find it easily, because we have the value of Kc, we have the value of water, we have the value of CO, we have the value of what? H2. The only value that is missing is what? Is CH4. So our job is just to plug the values in the Kc expression. So let's go ahead and do that. So when we plug the values, we are going to have something like this. We know that Kc is equal to 2.0 and H2 CH4 we don't have it. H2O we know that it's 0.2. So at the end we are going to solve mathematically in this way, and at the end we are going to find CH4 to be what? CH4 to be 6.91. So as you can see, it's just mathematics here that was happening. So on this question there was no use of getting a ICE table, because of what? The values at equilibrium are already what? Are already given. Let's go ahead to problem 2 or example 2. We have N2O4 is equal to 2NO2. So N2O4 has broken down to what? To NO2. Now we have been given the initial concentration of N2O4 is what? is 1.00. The initial concentration of NO2 is what? 0.00, and the Kc is 0.25. Now, what's our job here? What have we been given to find? What we need to find is what we call the final concentrations, or the concentrations at equilibrium. Just as you saw in the previous example, they were already given, but here they were not given. Now, this is where the ICE table comes in. Just as I said, you use the ICE table to find the final concentrations given the initial concentrations. So let's go ahead and write the ICE table. So that's the ICE table for this reaction. As we can see, N2O4 is a reactant. That's why on C, which is change, it's negative X, because the coefficient of N2O4 is negative. What about NO2? The coefficient is positive 2 because it's a product, so it's going to carry a positive charge, and its coefficient is 2. At the end, the values at equilibrium, we have 1 minus X for N2O4 and 2X for what? For NO2. Now, what do we do to find the value of what? The final concentrations at equilibrium? Again, we write the what? The Kc expression. So when we write the Kc expression, we have 0.25 as what? As the equilibrium constant. Then products, we have 2x power what? Since it's carrying a 2, it has a coefficient of 2, it's going to be squared. What about down? It's going to be over 1 minus x. Then we use this, we solve the quadratic equation, or we solve this expression, and we find the value of what? We find the value of x. Let's go ahead and solve for x. When we solve for x, we are going to see that it's going to lead us to 4x squared plus 0.2x minus 0.25, which is equal to 0.5. And this factor factors nicely, which is a perfect square. And when you solve it, you are going to find that x is equal to 0.25. Now, when we have found 0.25, does that mean it's our final answer? No. Our final answer, we want the values of what? At equilibrium, the final concentrations. We know at equilibrium, N2O4 is equal to what? Is equal to 1 minus x. So how do we find the value of N2O4 at equilibrium? We just say 1 minus 0.25, which is equal to what? 0.75. So this is our answer. This is our final concentration for what? For N2O4. What about NO2? NO2 at equilibrium, we know that NO2 at equilibrium is given by, so NO2 at equilibrium is given by, it's given by 2x. So what do? We just multiply 2 times 0.25. At the end, we are going to have, the answer is going to be what? Just multiply the 2, you are going to have 0.5. So at the end, these are your values for what? The final concentrations at equilibrium for N2O4 and the NO2. So that's how we solve that's how we find what final concentrations when given the what? When given the initial concentration and the Kc. Now, here when we're doing the, here on this Kc expression, sometimes there is a point where 1 minus x, instead of using solving it, sometimes it can be quadratic equation. As it leads to quadratic equation, there is an assumption we usually use, whereby we just remove the x so that we remain with what? With only 1. So we are going to do an example on that one, so that you see when to use the what? The assumption. And most of the question that comes in the exams, we use the what? That assumption. So here is the problem, which is example 3. We want to use the assumption, and that assumption we usually assume that x is small. So the reaction is as follows. We have hydrogen and iodine reacting to form 2HI. So what are the concentrations? These are the initial concentrations. They are there on the screen. So I'm sure now you are familiar with the ICE table. You know the next thing we do is just what? It's just writing the ICE table. So when we write the ICE table, we see that H2 is a reactant as a coefficient of 1, so it's negative, and same applies to I2. What about HI? HI is just positive 2, and at equilibrium for H2 you are going to have 0.5 minus X. Same applies to I2. So now how do we find the value of X? Now that's where the assumption, you want to see the assumption. So we go ahead, we write the KC expression. So that's the KC expression. Now for the assumption, we assume that X is small. What do? We are going to remove the X, just bring it something like 50 is equal to 4x squared, something like 0.5 times 0.5, something like that. We want to remove those minus X and minus X. So what do? So there we go. We remove the X we are going to have, and our value of X is going to be 1.77. So what did I do there? So I just multiplied 50, first 0.5 times 0.5, multiply again by 50, then over 4x, or over 4. Then we are going to have X squared is equal to 12.5 over 4. And try to punch your calculator. You are going to find that the answer is 3.125. Now what's the square root of 3.125? It's 1.77, and we get the positive value. So now how is the assumption? Now here we just assume that X is too small, and we can just ignore it. Now how do you prove if our assumption is right or wrong? So we prove that. So how we prove the assumption? We check. And how do we check? We say the X over the initials. For example, the initial for the reactant, which was 0.5. Now when you say 1.77 over 0.5, you are going to find that the answer you are going to find is 3.54. And this one, we are going to see that it's greater than what? The 5%. So therefore our assumption is going to be invalid. So we must solve using quadratic equation. So we were not supposed to use the assumption, because now when do we use the assumption? We use it when Kc is very small. For example, something times 10 power negative 2, or very large, or initial concentrations are large. Also when X is less than 5% of initial value. So don't use it if the 5% rule fails. So thank you for watching. If you have come to the end of this video, and don't forget to like and subscribe. So see you in the next video.